Welcome, my friends, to my video on generalized functions and weak derivative. This video is not part of any of my regular courses, but recently I had a conversation with a friend about generalized functions and weak derivatives, and that inspired me to make a short video on it to just explain the concepts a little bit. And I'm not going to give a full proper course on it here, but I just want to be a bit sketchy and convey the main ideas that underlie generalized functions and weak derivatives, and also show you some examples. Now, the theory of generalized functions, which are also known as distributions, was developed in functional analysis to study partial differential equations that do not admit solutions in the classical sense. So there are no normal functions that solve these differential equations, but in this sense of generalized functions, they might have solutions after all. So what I want to do here is to introduce this concept of generalized functions, and I want to explain how weak differentiation works. So you can take differentials of these generalized functions in a certain sense. Of course, you would have to if you want to treat differential equations with this concept. And this concept of weak differentiation extends the usual derivative that you know from ordinary functions, and it will apply to a larger class of objects. Now, I assume a few things here that you should know when watching this video. First of all, you should be familiar with the theory of vector spaces, so linear algebra. Over a field K, I assume here that K, the scalar field, is just the real numbers, but what I say also would make sense for the complex numbers. You should be familiar with the concept of dual vector spaces, so V star, if V is the original vector space. And the dual vector space is the space of linear maps from V into the scalar field, so into the real numbers here. They are also known, these dual vectors, as covectors or linear functionals. And in finite dimensions, you could think of this dual space V star as the space of transposed vectors. You should be familiar with the fact that certain classes of functions form vector spaces. For example, the continuous functions, but there are also many others. And they form a vector space simply by taking two functions and adding them pointwise or multiplying them pointwise by a scalar, and in that way you satisfy the vector space axioms. And you should be familiar with some standard differential and integral calculus. Mainly integration by parts is going to be an important tool in this video. So let's begin with introducing test functions and generalized functions. In order to make our construction of generalized functions, we need an additional vector space, which I call T, and we will construct our generalized functions as the elements in the dual space T star of this auxiliary vector space T. Now, T itself is not that interesting to us, but we still need to define it properly so we get a good dual space T star. And we define T as the vector space of test functions over the real numbers, hence T. And a test function is a function phi with the properties that phi maps real numbers to real values. Phi should be infinitely differentiable, so contained in the vector space C infinity over R. And very important is that phi has a property that's sometimes called compact support. That means phi is 0 outside of a compact interval. So in particular, this means for large values of x, or absolute values of x, phi of x is always equal to 0. And what follows from that is in particular that phi of x goes to 0 for x to infinity. This property will be very important when we look at integration by parts later on. Now, we could define these test functions on Rn, so for multiple variables or on just some subset of it, but this is just a technicality. This is not really important for understanding the concept to have this generalization here, so I will keep things simple and just stick with functions defined on R. Here's an example of a test function. So this phi of x is defined to be e to the power of 1 divided by x squared minus 1 when the absolute value of x is less than 1. And outside of this interval minus 1 to 1, it is defined to be 0. So it looks something like this. So it's practically 0 everywhere except for a little bump here between plus and minus 1. And yeah, this is a pretty good example for such a test function, and it would even be good enough if we chose our vector space T of test functions to simply consist of this function and all of its scalings and translates. But from the general definition of test functions, of course, there could be many more functions than just these bumps. Now, by T star, we denote the topological dual space of our space T of test functions, where topological dual refers to it being the linear maps going from the test function space to the real numbers that are also continuous. So this is a technicality in functional analysis that you usually require. It's not really important for us here, but just to keep things proper, I asked for these linear functionals to be continuous. And the elements of this dual space T star are called the generalized functions, or often they're also called distributions. Now, we have a nice correspondence between continuous functions and certain of these generalized functions, of these linear functionals. So if f is a continuous function over R, then we can construct an element which I call f star in this space T star by doing this. F star applied to a test function phi is given by the integral from minus to plus infinity of f of x multiplied by phi of x over x. And you can check that this is indeed a linear functional because, well, simply because the integration is linear in this function phi here if we fix f. We could define such an f star for a broader class of functions than just the continuous ones, but I do not want to deal with the technicalities that this might incur, so with the continuous functions we have a neat definition here and don't need to worry about anything. Now we have this association here of a function f, a continuous function f, with its functional f star, and this gives us an embedding of the vector space of continuous functions into this dual space T star of generalized functions. I call this embedding simply star, and yeah, it simply consists of mapping f to f star. And this is in fact a one-to-one mapping onto the image of the continuous functions in T star. So we may in fact identify any continuous function f with its corresponding linear functional f star. So we can pretend that the continuous functions live inside of T star. So here's a picture to sketch this. So here's the space of continuous functions. We have an element f. This map star here maps it to f star, and we can actually replicate the space of continuous functions within this vector space T star of generalized functions. But there are elements in T star that are not contained in the image here of the continuous functions. That's important to be aware of. And we will see such an element in a few moments. Now let's introduce weak derivatives. We assume now that our function f is even differentiable, where we denote the derivative by f prime, so that's just df by dx, so f taking the differential with respect to the variable x. And now we use integration by parts to find that for any test function phi in our test function space, we have the following. If we take the start version of the derivative of f prime and apply it to the test function f, then by definition, this is the integral minus infinity to plus infinity of f prime x times phi of x over x. And integration by parts applied to this integral here gives us that this is f of x times phi of x taken with the boundaries or the limits plus infinity and minus infinity minus, now the the derivative switches from f to phi, so minus the integral from minus infinity to plus infinity, f of x times phi prime of x dx. And notice phi prime exists always because we assumed our test functions to be infinitely differentiable. But this here is merely this second term here. So ultimately the phi prime star of phi is just minus integral from minus to plus infinity f of x times phi prime of x dx, because this part here vanishes due to the fact that the test function phi becomes 0 for large values of x. So if we take this expression here and the limit to plus or minus infinity, then each time it will be 0. So this bit disappears and we're left with just this part here. So in summary, if f is differentiable, then f prime star applied to phi, the linear functional for f prime, is given by minus integral minus infinity to plus infinity f of x times phi prime of x over x. And looking at this equation here, we make a crucial observation. This part here depends on f being differentiable, because only for differentiable f we can write this functional down, f prime star. But the right hand side does actually not depend on f being differentiable. So this expression here can be written down for any integrable function or any function where this integral here exists. And this leads us to defining the weak derivative, which I'd call df, of any integrable function, so not necessarily a differentiable function, to be the linear functional df in t star given by df applied to a test function phi is minus integral minus infinity to plus infinity of f of x phi prime x dx. And as we've just seen on the previous slide, this definition is consistent with the classical derivative f prime for the differentiable functions. So if f is indeed differentiable, then this weak derivative does correspond to the actual derivative of f, just with the star applied to it. But yeah, as I said, we want to simply identify the continuous function f with their images in the test function dual space. So yeah, for usual differentiable functions, this gives you just what you would expect, but you can define this even for functions that are not differentiable. And now we can play this game even further. Observe that for an integrable function f, this expression here is nothing but minus f star applied to phi prime. So the right hand side here makes sense for any linear functional L in t star, even if it's not the image of some normal function within t star. So we can define this weak derivative on all of t star via this formula here. So if L is any linear functional in t star, we define the weak derivative dl applied to a test function phi is supposed to be minus L applied to phi prime. This is all a bit abstract and maybe confusing, but let's work through some examples to see what actually happens. And to get something out of those weak derivatives that we wouldn't have with ordinary derivatives, let us first apply this notion to some non-differentiable functions. A nice example of a function that's not differentiable is the absolute value function, so I call it abs here. That maps all real numbers again into the real numbers, or into the positive real numbers to be precise. And the precise definition is x is mapped to its absolute value, which is minus x for the negative numbers and simply x itself for the non-negative numbers. This function is differentiable everywhere except at x equal to 0. And if we think of the derivative geometrically as the slope of this function, then we would expect the derivative, abs prime, to have constant value minus 1 everywhere here because it's going downwards with a constant slope. Then to make a sudden jump from here from minus 1 to plus 1 at x equal to 0, and then continue just having constant value plus 1 for the positive values of x. And let's compute the weak derivative of this absolute value function now and see if it actually reflects this intuition. We identify our absolute value function with its image in the dual space T star of generalized functions, and then we can compute the weak derivative of the absolute value for any test function phi. So weak derivative of abs evaluated at phi is by definition minus abs star applied to phi prime, and this is minus integral minus infinity to plus infinity absolute value x times phi prime of x dx. Let's compute this. So we will use again integration by parts in this computation. So this expression here, which was just this one, we first split it into the integrals over the negative and positive numbers. So we have the two areas of definition for the absolute value separate. So the integral over the negative numbers is minus integral minus infinity to 0 of minus x times phi prime x dx. And then the integral over the positive numbers, together with the minus sign here, is minus integral from 0 to infinity of plus x times phi prime of x dx. Now we cancel out the minus signs here and just get for this part here the integral of minus infinity to 0 x phi prime x dx. And then we can evaluate each of these two integrals here through integration by parts. This one becomes x times phi of x evaluated from minus infinity to 0. And again we observe that this is 0 because at the boundary 0 this factor x becomes 0, and in the limit to minus infinity phi of x is 0. So in both integration limits here this expression is 0, so this disappears, and in the same way the corresponding part in the second integral disappears, and we are left with minus integral minus infinity to 0 of phi of x dx plus integral 0 to infinity phi of x dx. And now we combine these two parts into the following, into the integral of minus infinity to plus infinity over a function h of x times phi of x dx. And this is the same as h star applied to phi. And the function h is simply defined like this. H of x is minus 1 for negative values of x, so that corresponds to this minus here, and it's plus 1 for positive values of x, so that corresponds to this part here. And this function, I call it h because it's called the Heaviside function. And a lot of people think it's called the Heaviside function because it somehow drops to minus 1 for the negative numbers, but that's not true. It's actually named after a physicist named Oliver Heaviside, who lived in the 19th to early 20th century. The Heaviside function here, we see the graph, so it's minus 1 for the negative numbers and it's plus 1 for the positive numbers. And this does satisfy the properties we intuitively wanted to have for the derivative of the absolute value. So for the negative numbers, we have a negative slope, constant negative slope minus 1. That's reflected by this value here. For the positive numbers, we have a constant positive slope plus 1, reflected by this constant number here. And at 0, we make a sudden jump from slope minus 1 to slope plus 1. And this is reflected in this discontinuity of the Heaviside function at 0. So yeah, the weak derivative quite nicely reflects our geometric intuition about the derivative of non-differentiable functions. The absolute value was a non-differentiable function, and the Heaviside function is even a non-continuous function. So in particular, it's not differentiable at 0 in the classical sense. And our intuition here for the derivative of the Heaviside function would be that it's 0 everywhere except at x equal to 0, because, well, here it has a constant value, so the slope is 0. Here it has a constant value, so the slope is 0. And only at x equal to 0 something happens. So here there would have to be some infinite slope going up from -1 to +1 that allows us to get from zero slope here again to zero slope here, but have an infinite jump that goes from minus to +1. Now let's compute the weak derivative of the Heaviside function. So you could think of this as the second weak derivative of the absolute value. So dh applied to a test function phi is by definition simply minus h star applied to phi prime, and this is again minus integral minus infinity to plus infinity Heaviside function x times test function prime of x over x. We evaluate this integral here. So this becomes the following. If we split again into the negative and positive number parts, then we get the integral from minus infinity to 0 of minus phi prime of x, because here the Heaviside function is -1, so we get this minus sign. And then for the positive part, where the Heaviside function is simply 1, we get, with the minus sign here, we get minus integral from 0 to infinity of phi prime x dx. And here we can simply integrate phi prime after cancelling the two minus signs here. So we get phi of x in this integral in the boundaries of minus infinity to 0, and here we get phi of x in the boundaries from 0 to infinity. Again, recall the test function phi in the limits to plus or minus infinity is 0. So what we're left with here is phi of 0. And what we're left with here is minus phi of 0. So again, plus phi of 0. So this is phi 0 plus phi 0. So the derivative of the Heaviside function becomes 2 times phi evaluated at 0. So in summary, this is the weak derivative of the Heaviside function applied to a test function phi. It's simply the linear functional that takes the test function and maps it to the value 2 times phi at 0. And this weak derivative dh of the Heaviside function is no longer a function in the usual sense. So here we have a true distribution, and this is actually a very famous one. So the derivative of the Heaviside, the weak derivative of the Heaviside function is twice the so-called Dirac distribution delta, or also called the delta distribution, which is simply given by delta of phi equal to phi evaluated at 0. So this linear functional takes the test function and maps it to the value test function evaluated at 0. And physicists and engineers often like to treat this distribution as if it were a regular function, but with some rather magical properties. Namely, they define the delta function in heavy quotation marks to be the function that is 0 everywhere except at the point 0. And at x equal to 0, its value should be infinity, and this mysterious value infinity should be just big enough that when we integrate over delta x combined with the test function, so basically taking delta star of phi integral minus to plus infinity delta x phi x dx, then, well, because delta is 0 everywhere except at 0, this becomes, again, heavy quotation marks, the integral from 0 to 0 over this value infinity times phi of x. And then the intuition is that this should just be phi of 0, so that the 0 length integration interval, but multiplied with this strong value infinity, somehow is just big enough to evaluate this one value phi of 0. Now, as I said, this is all to be taken with a grain of salt. Delta is not a proper function, so this is some hand-waving intuition that we have here, but it's not actually a proper formula. So be careful when you write something like this down. Now, as I said, such a function, delta, does not exist, so it is a generalized function that is not a proper regular function. However, this intuitive picture is satisfied if we think of it. It's 0 everywhere, except at 0 where we have this infinitely large jump. So that satisfies our intuition that we had for the Heaviside function, where we had to have this infinite slope at x equal to 0, where we jumped from -1 to +1 constant values. And just for the fun of it, let us compute one more weak derivative, namely the weak derivative of the Dirac distribution. And this is surprisingly easy. So the weak derivative of delta applied to a test function phi is, by definition, minus delta applied to phi prime. And by definition of delta, this is just minus phi prime evaluated at 0. Yeah, and from this you may guess what the higher order weak derivatives of delta are. And that's it. This is my short introduction to generalized functions and weak derivatives. So I hope you got a bit of an idea how that works, how you get the identification of first ordinary functions with linear functionals in the dual space of the test functions, and then how you can use properties of this identification to motivate the definition of the weak derivative, and how you see that this weak derivative does actually reproduce some geometric intuition that we might have about the slope, in quotation marks, of non-differentiable functions. And thank you for your attention, and please like this video and subscribe to my channel.